Okay, so which one y'all want to work?
Apparently, all of them. The ones I thought I had right, going to the key. Your key could be wrong, but
It'd be hard for us to be wrong because we've been teaching this class for quite a while. It wouldn't surprise me. That's happened to me before.
like, apparently the ones I thought I had right, I got wrong. I definitely thought I had.
Okay, so we start off with the first one. It's decimal. We got 297. So I'm gonna start writing the chart. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. I'm gonna write a big chart because we got a bunch of them to convert. What's the biggest one we got to convert? 1024, 2048. We can always add one. So what I'll do is I'll come up here and I'll see what is the highest decimal equivalent of a power of 2 can I use. The best thing I can do, the biggest I can do is 256. So I'm going to put a 1 there, and I'm going to come over here and I'm going to subtract 256 from there. What does that leave me? Okay, it leaves me 31. Can I get a 128? Can I subtract a 64? Can I subtract a 32? No. Can I subtract a 16? Yes. Subtract the 16. What does that give me? So that would be 15 right there. Are we okay?
Keep that.
I don't have a copy of the key. What? Oh, okay. So anytime something happens while we're going along, I'll need to make sure that we catch it before I keep going, right? So there's 41, right? And we subtracted a 250. So as soon as it comes up wrong, because I'm just doing what y'all telling me to do, right? So 41, we can't do a 128, we can't do it, but now we can do a 32. And what does that give me? 9. So that's going to be 0, 1, 0, 0, 1. Okay, so that's binary, right? You understand? Everybody okay? Any questions? So what I'm going to do now, I'm going to go to octal. I'm going to take this binary number, I'm going to split it up into groups of 3s. And so this will be a 4, this will be a 5, this will be a 1. That's base 8. This is base 2. Everybody okay? See, I did that. Any problems? We okay?
Yes, well,
Huh?
I won't write the chart. That's how I was the chart on the paper.
And then I'll come up here. Oops. And let's get rid of the green. Now for hexadecimal, what I'm going to do is I'm going to split this into groups of 4s. Same number, split it into groups of 4s. 1, 2, 3, 4, 1, 2, 3, 4. And then I'll come over here and convert that over in groups. So it's going to be a 1, that's going to be a 2, that's going to be a 9, and that's base 16.
Just a 1 by.
Yeah, what we do, what in your head, what you got to do is you've got to go in groups of 4s, and you got to start with the least significant digit. You just can't start anywhere, because if I put a 0 on this side, it's going to change the way the number. But I can put as many zeros over there as I want to. So what I'm doing in my mind is I'm picturing those zeros over there, because I've got to go in what? Groups of 4s. Of course, I've been doing it so long, I can envision it out. I can envision them out there. Why can't you? This is why you got to start when you split these things up. You got to start at the least significant bit, Because I can't come over here and do a group of 4 over there and a group of 4 over here and then stick zeros on that side because it changes the weight of the number, right? So it's like I've got a number, 10. Well, I can put as many zeros over here as I want to. And it don't do what? It don't change the weight of the number. But I can add zeros on that side because that changed the weight of the number. It moves me over a whole power of 10, right? You understand? So to complete the group, and this is why when you set these groups up, you always start setting them up from the what? From the least significant bit, which would be this guy over here, right? Everybody understand that? Yes or no? What's that? You should have been here in class. What we do now is we come up here and we use this 1, 2, we use this 1, 2, but we're doing it up here. So what I'm going to do is I'm going to come up here and split this up. And we're going back to groups of 3s, right? Now, of course, I've been doing this so long, and it's not hard. What I'm doing, and now I'm envisioning this as 1, 2, 4. 1, 2, 4. 1, 2, 4, right? You understand? So I've got a 1 under the 4, so I wrote down a what? 4. I've got a 1 under the 4, and I've got a 1 under the 1, that's 5, so I wrote down a 5. And of course here I've only got a 1 over that, so I wrote down the 1. Now on base 16, what we do is we do what? We do groups of 4s. One, 2, 3, 4. 1, 2, 3, 4. And then I'm thinking what? 1, 2, 4, 8. Then I start over again, right? 1, 2, 4, 8, 1. Right? You understand? So I got a 1 right here. I got a what? I got a 2. And over here I've got an 8 and a 1. We add those together and that gives me a 9. Did the light just come on? Same thing we did in the other class, right?
What I did was, at the end of all that, somehow I ended up adding all the numbers together.
Now, what we're doing is we're directly representing about. I don't need to do any math, right? So I've got these 1, 2, 4, 8, 1, and I've memorized these patterns. So I don't even think about it anymore. I know that pattern. I know this pattern right here is a 9. I know that pattern right there is a 5. I know that pattern is a 2, and I know that's a 1, right? Understand? And that's what you got to do. Our problem, our intent of doing these bases is not to have to do any. The only math that we need to do is when we do this. After that, we should be able to go between binary and octal or binary and hexadecimal without even thinking about it, without even doing a calculator. And that's why we use hexadecimal. That's why computers display binary information in hexadecimal. Because all the computer is doing is turning on dots, right? You know, 1s and 0s. It processes information. So it can make that pattern. It can take this pattern right here. And this is what it'll display.
Are we turning these in?
No, y'all keeping these. Y'all. That's what I did, right? That's the way I grade them. Okay. So worksheets, you're not graded by correctness. You're graded by trying to do, and you need to do every one of them. So from now on, if you don't attempt some of them, I'm gonna start reducing the grade, right? You understand that? So you need to attempt all of them, right? Does that make sense? So the next one, everybody okay so far? Okay, so the next one, I'm leaving my chart up there. We're going to be using that chart a lot. And how do you do on that? And to me, of course, you're going to have that number system conversion, but then all you do is you start with 1 and just do what? Just double it every time. That's all you do.
As you can tell, I did okay, but when you get one wrong, it spirals on down from there.
Well, on a test, that's what I'm going to look at. So what I'll do is if you get one wrong, but but you convert it the rest of the way, then you'll just lose the point on the one you got wrong. And that's the way you test a grade. Because you're doing the conversion right, and that's just like when you take electronics classes like DC or stuff. That's the way the instructor should have graded, because you got Ohm's law, and so you miscalculate V, and then V's in the rest of your formulas. So what would you do? You carry on, and that's why that's why in DC that's why in DC and doing this, it's not gonna be multiple choice. You're gonna do it longhand. Because if I was to put it multiple choice and you miss this one, what would happen? And then the test would count wrong. So that's why on DC and solid state and stuff like that, where one answer depends on the answer of the other one, we do those in pencil. We make y'all do those. So here I got a binary number. Now, just to make sure I got it right, I'm going to start on the least. Well, what I'm going to do is I'm going to go ahead and split this into groups of, I'm going to go ahead and split this number into groups of 4s, so I can copy it over, so I can do it in my head. One, two, three, four. 1, 2, 3, 4. So that's going to be, the hex is going to be what? C, D, F. So is that right? I get it right? Oops, no I didn't. I left out a 0. Where did I leave my 0 out again? Is that right? Okay. So what I'm going to do now, I've got my binary, so I'm going to convert it to decimal. Well, I could go ahead, what I might do is I'd go ahead and convert it to, I think, hex. I've got it in hex. So this will be what? C, D, F, right? Everybody okay?
That was part of my confusion of how to actually use the alphabet.
Okay. First thing we got to do is we're going to come up here and we're going to, and you got a chart down there. Of course, like I said, I've done it so long, I know it. So I'm going to come over here now, I'm going to put a chart. So look in y'all's chart. Look in y'all's chart for hexadecimal. Okay. Right? And I'm looking at this pattern. I'm looking for this pattern right here. Or in my head, what I'm doing is I'm doing 1, 2, 4, 8. Okay? You'll see that. And that equals to a 12. Well, I can't put a 12 down as a single digit.
So that's hex is 1, 2, 4, 8.
Yeah, hex is 1, 2, 4, 8. Octal is 1, 2, 1, 2, 4. 1, 2, right here. Here's a pattern where here's a group of 4 right here. And what is it? 1, 2, 4, 8.
I thought that was power of 2.
It is powers of 2, but it's the decimal equivalent of powers of 2. Okay. So what we're doing when we're going to hex, we make it a little easier, because now we're dealing with powers of 16. So what we're saying, powers of 16, what we're doing with is we're dealing with 16 combinations, right? You understand that? Everybody okay? 16 and that's what the base is telling you. It's telling you, well, it's telling you what the weight of each other is, what the weight of each digit holds, but it's also telling you how many numerical combinations you have for a digit. So if I was to come over here and write down my numerical combinations, 0, 1, if I was to come up here, I'm going to do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, What do I put? What comes next? Yeah, A, B, C, D, E, F. Oops. I got into my thing down here, so. Gonna erase all of it, guys. I might have to shift it up. So there's my 16 combinations. Now, if I can come up with a certain number of binary bits that gives me exactly 16 combinations, then we can represent each digit with 4 binary bits. Okay. So what we can do to calculate the number of combinations that's available under any base, we can take the base and raise it to the number of digits. Now this gives me the number of numerical combinations. Now remember, one of your combinations is 0, right? You understand? Now the biggest number I can possibly represent would be x to the n minus 1. And this gives me the biggest number I can represent with a certain number of bits. So I come up here and I say base 2, 4 bits. What's 2 to the 4th when you look at your chart? 16. 16, right. That's exactly. So over here I've got 16 combinations. I can represent 16 combinations with 4 bits of binary. Exactly. So what that gives us the ability to do is to represent every hex digit with 4 bits of binary, or every 4 bits of binary with a hex digit. So those patterns we would have, so a 0, I would represent it like that. A 1, I would represent this like this. So now I'm only dealing with what? 1, 2, 4, and 8. This would be a 2. This would be a 3. This would be a 4. This would be a 5. This would be a 6. This would be a 7. This would be an 8. This would be a 9. This would be a A. This would be a B. This would be a C. This would be a D. Oops. This would be an E, and this would be an F. So we'll use a small binary number just to let you see how this works, and it's so cool. And this is the way we can do it with octal also, because 2 to the 3rd is 8. And in octal I have 8 combinations. So I can come up here, I'm going to take a binary number. And I would come up here and I would find this in my chart. This is an A, right? And this is a 5. Now, if I come up here and go through all this trouble, 1, 2, 4, 8, 16, 32, 64, 128, or okay, everybody okay? Convert this over, I'd say 128 plus 5. Oh, I'm sorry, I left out 32. Duh. I was thinking about something else. 128 plus 32 plus 5. And what does that give me? That's page 10. Now I'm going to take this, and it's going to be a little easier. I can do this in my head, by the way. But what I have to do to get it in a decimal equivalent, I have to come up with a decimal number on base 16, I have to get everything in decimal. So, of course, I know this would be A5. This is going to be 16 to 0. This is going to be 16 to the first. Okay. So I know 16 to the first is going to be 16. I know A is equal to a decimal 10. So that's going to be 10 times 16 plus 5. And what do you get? 165. So what we did is we just proved that if I split this thing into 4 binary bits, then I write those down as a hexadecimal number, that A5 is equal to 10100101. But if I was going to convey this binary number to you, which would be easier for me to give it to you, is A5 or is 1010101? A5, because it's less digits, right, that we're having to deal with. And they're not repetitive. They're not ones and zeros. So when the computer is trying to display this big binary numbers, so I mean, this is what we was talking about. So I could, and you could convert this number over. You can do it if you want to. But I could come up with any number, any binary number, and I could go to hex. And if I gave this number out, nobody in this class would get it. Now, if I wrote it up here, that's fine, right? You understand, because you got time. But if I called it out to you. So what I'll do is I'll come up here and I'm going to take this sucker and I'm going to split it into 4 binary bits. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. If I don't have 4 binary bits over there, I just can add zeros, right? You understand that? Then I look at the pattern. So look the patterns up. What would this be? In fact, it would be a B, right? What would this be? A 5, 6, 8. Right? Base 16. And I guarantee you, if you converted those numbers over, you would get exactly the same answer. So what we did in class the other day is I brought up my fancy calculator, which you're not going to be able to use on the first test, right? Huh? Not this, because am I using a calculator? No, you shouldn't use a calculator at all, because all you're doing is you've got that chart, right? I'm going to give you the chart that gives you your powers of 2. So you don't even have to remember 1, 2, 4, 8, 16, 32, 64, 128, 256, right? 512, right? 1024, 2048, 4096, right? 8192, right? 16,000. Yeah, but understand, but why do I know those? Because I've been, right? So what we're saying is that you don't have to remember that. You don't have to remember your 16 multiplication tables. And I'll show you, that's really cool. We don't ever use division in this. We're going to use subtraction and addition. If you decide you want to do addition, you're going to have to do it longhand. That's your call. I mean, like I said, you can divide by 2 if you want to. You can divide by 16 and keep up with the remainder and come back and multiply by 16 if you want to. Right? You understand. Or you can go through the binary number system by using either one. By repetitive subtraction. And everybody in here can subtract, right? If you can't, then you don't need to be in college, guys. And then I can take, and if let's say I wanted to give you a big binary number. Well, I can come over here, I can say C95B3. And this is base 16. Well, I would write down the pattern for a C. Oops. I'd write down the pattern for a C. I'd write down the pattern for a 9. I write down the pattern for a 5. I don't drop any zeros. You can't drop zeros in here. The only place you can drop zeros is over here, right? You understand? You have to write down the entire 4-bit pattern. There's a 5, there's a B, and there's a 3. Oops, there's a 3. So what I did is I can go between base 16 and base 2 without even what? And after you learn those patterns, guys, and those are only 16 patterns you have to learn. If you're really going to get into computers or you're really going to get into programmable controllers, you need to learn those patterns. Because I can tell it to do a logic operation and I can enter it in decimal. But what I would have to do, logic deals with binary. I would have to take my binary number, I'd have to convert it to decimal and enter it in decimal. Well, the PLC allows you to enter information in hex. So if I can go between the binary number I want and the hexadecimal number I want, I don't have to go to decimal, right? You understand that? So if you're going to deal with computers, and if you're going to deal with networking, and you've got to figure out a subnet mask. The subnet mask you enter in your computer is binary. I'm sorry. The subnet mask we enter our computer is decimal. But to come up with a subnet mask, you got to know what? Binary. If you can't do that, then you can't set up networks. You can't set up a TCP/IP protocol, which is the protocol of the internet. So you'll never be able to do networking. You'll never be able to trace a circuit. You'll never be able to figure that out. So if you're going to deal with computers and you're going to deal with programmable controllers, then this is the base you need to learn. Octal, like I said, why do we learn Octal? Well, we learn Octal because that's the first language, that's the first numbering system that PLCs allowed us to use besides binary. So when we enter information into a PLC, we got 3 bases. I'm sorry, we got 4 bases we can deal with. We can enter it in binary. We can enter it in decimal, we can enter it in hexadecimal, or we can enter it in octal. So all of our numbering systems that we have is available to you. Now I know you like decimal because that's what you dealt with all your life. Now hexadecimal, octal, how many patterns do we have to learn? Octal, how many patterns do we have? Just 8 patterns, right? Yeah. So that's what's nice about octal is octal you don't have to memorize 8 patterns. 16 patterns, you just got to remember rise 8. So that means I could come up here now and I could write an octal number, and we should be able to do the same thing. 7, 3, 6, 4. Well, I would write 7, 3, 6, 4, and that would be my binary number. We can convert those, and those would be exactly equal to each other. But which would be better for me to give you? The problem we have is that when I see a number by George, we need to know what base. So 7, 3, 6, those combinations of digits is legal in 3 bases. It's legal in what? Decimal. It's legal in hex, and it's legal in octal. It's not legal in binary. So this is where sometimes we get into trouble. So what I'm going to do is either on a test it might say convert this octal number to binary, but when I write something up here, I'm going to subscript it so you'll know what base we're dealing with. That don't mean anything. That's just telling you the base, right? Now if I was to put it up here, it would mean something, right?
So you had 16. Right over that table.
That would mean that's the base 16.
We would break that down to 4.
Yeah, so I could take that. You break it out in 4. So you're right. So let's do that. So that's octal. But the weight's going to be different, right? Because with base 16, I get 16 combinations. So it's going to make the binary number a lot bigger. And that's why I got to make sure that I identify the base. So that would be legal in all of our bases. That's a legal number in decimal. That's a legal number in hex. But if I was to come up here and write down a 16, then we would do a 7. I would do a 3. I would do a 6, and I would do a 4. You can see it's a lot bigger. You can see it's a lot bigger number. So base 16 is really efficient, which means we can represent extremely large numbers with a lot fewer digits, right? You understand? So your computer's going to do your computer does that hexadecimal. And this is where we're showing. So this is this computer. You can do this. You can find this on any Windows computer, where this actually tells me what we. So the way a computer works, it's just like when I want to call you, you're assigned a telephone number, right? You understand? And if I want to talk to you, then I have to know your number. If I want to talk to somebody else, I have to know their number. So that would be like in here, if we were computers, the only way I could talk to you is by calling your phone. And nobody could hear my conversation. That's the way computers work. So it only talks to one thing at what? One time. So everything in the computer is assigned an address. So if we was to look at the pinout of a microprocessor, we'd see one of the big, we call it a bus, would be what we call the address bus, where it outputs a binary code on the address bus. And then the device that's got that address is the only device that the processor is going to communicate with any one time. So I would think I showed y'all this. So we can go to memory resources, and this is the memory resources right here. And now these are extremely large binary numbers. So here's the address right here. So motherboard resets is from address F00000. So what base is that? It's obvious what base that is. Base what? All these. Yeah, we see L.
Base 16.
This is base 16. So what my computer is saying is that my high definition audio, the memory on my audio controller is between this address. Which if I was going to do the binary programming, I would need to know that. But we could go to just about any compatible computer and we would see that these devices are going to be at the same address. So that's why I can't go out and install an Apple operating system on a compatible computer, because the addresses would be completely different. And the operating system would have no idea where anything's at, right? You understand? That makes sense. Here's the I/O ports. Now this guy only uses it uses 16 bits. So we can keep going, but what base is it? So right here we don't know. As soon as I go down and see just what, see that A, I know what base it is. But it does it in the same rate. So that means this guy uses 16-bit I/O addressing. You'll know none of them gets over 4 digits. Which means this guy could technically have 65,536 I/O ports in this computer. And it don't need that many, right? Now memory could be big. How many digits is it using for memory? 1, 2, 3, 4, 5, 6, 7, 8. So that'd be base 16, that'd be 16 to the 8th. And this is how much memory the operating system supports. I think that's the address and range for the processor. That's how much. It used to surprise me. When Windows XP first came out, it could only address 2 gigabytes worth of memory, the operating system. But they came out with motherboards that could you could put 4 gigabytes of memory in. And people would go out there and stick more memory in that, and they were doing what? They was wasting money. Yeah. So because the operating system could only do 2 gigs. So I need to set my chart back up, right? And we'll spread it out a little further when I put it across the top. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. I think that's plenty for this worksheet. Okay, so the next one, they give me octals. So I'm going to say 75 octals, right? Which is going to be 111101 binary. Hexadecimal, I'm going to take the binary number and convert it into 1, 2, 3, 4. So that's, what is that? 3. Yeah, but there's no such thing as a 13 in hex. So you'd have to know a 13 is a D, right? There you go. And then decimal. So I could go 1, 2, 4, 8, 16, 32. So I can add 32 plus 16 plus 13, right? And that should give us our decimal number. We okay? Any questions on that? Is that okay?
Okay, so to get the decimal, all you have to do is just write the chart out overnight.
Just write the powers of 2. Now here we're dealing with binary. We're not doing groups of 4s anymore. That's hexadecimal. We're not doing groups of 3s anymore. That's octal. This is binary. So we have to do 1, 2, 4, 8, 16, 32, 64. Now to go to decimal, what we do is we add the bits that has what? 1s in it. We don't add the bits that has what? 0. The next one is 2A5 X 2A5 2A5. Everybody okay? 1, 2. I could go ahead and go to octal with this if I wanted to. One, 2, 3, 1, 2, 3, 1, 2, 3. That'll be a 1, 2, 4, 5. They say. Are we okay? Base 2, what am I going to do with base 2? I'm going to come up here and write the powers of 2 chart, right? The decimal equivalent of the powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. I'm going to add 512, 128, 32, and 5. This last group, What's that give me? And you got to be careful with this because you might see me do this every once in a while where I skip a power or two because I've already floated in my head, the next one. 677. You're right. I'm not doing the math. The next one they give us the decimal is 23. This shouldn't take very long. 23. Now I'm going to binary. I got my chart up there. I'm looking for the biggest decimal equivalent of powers of 2 I can subtract from this thing. What's the biggest thing I can subtract? A 16. Write a 1, and people forget to do that. When they subtract, they forget to do what? Write the 1. So the biggest mistake we have here is people trying to subtract that from that. Right, you understand? But what you're trying to do, you're going from here to there. So what you're doing is you're subtracting the power of 2 from the what? From the decimal number. And I don't know what to do about that. So what's 23 minus 16? 7. Everybody okay? 7. If I wanted to go to octal, I would take that number and I'll split it into groups of 3s. 1, 2, 3. I'll imagine there's a 0 on that side, so it's going to be a 27 base 8. Right? I'll come up here to go to octal. I'm going to hex. I'm going to split it up into groups of what? 4. I pretend there's 3 zeros over here, and that's going to be a 1, 7 base 16. And we started out with somebody on this worksheet actually put spaces on the binary number. They shouldn't have done that. It makes it a little easier for you to write down with those little spaces. Okay, did I get that right, guys? 4, 3, 5. Of course, what I could do, you don't have to do these in any order. I could go ahead and split it into groups of 3s. This is going to be a 4, 3, 5, 1, base 8. Right? Everybody okay? You already know how to do this, people? You got any problems with this? I don't see you writing or anything down there. It's going to be interesting to see what you make on the first test. So this would be an 8E9 base 16. Everybody okay? See how I did that? What's that? what we're doing now, once we go into hex, we're not looking at the 1, 2, 4, 8, 16, 32, 64 anymore. We're going 1, 2, I'm sorry, backwards, guys. Don't let me do it. We're doing 1, 2, 4, 8. 1, 2, 4, 8. 1, 2, 4, 8. Now what you gotta know is these. So in hex, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the numbers in the hexadecimal number system. So you got to know the decimal equivalent. Now these are the same, right? You understand that? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What you got to know that A is equal to a decimal 10. B is equal to a decimal 11. C is equal to a decimal 12. And D is equal to a decimal 13. Well, what I got right there is I got a 13. I cannot, in a numbering system, you have to represent each number with numbers up to their base with a single digit. So instead of writing 13 for that group right there, I wrote down a what? I left off E, and then F would be what? 15. So instead of writing down 13, I came and put what represents the decimal 13 in the hexadecimal number system. What's that?
You got 18, 9. Yeah.
Oh, okay. Thank you. I didn't do that. I just added that up wrong. I knew it was an E. This is where I made my mistake at right there. I understand that now. This is octal. That's what we're through with this. We're working on this one now. So that would be the pattern represented in octal. So 4, 3, 5, 1 would be that binary number represented in octal. 8, E, 9 would be that number represented in hexadecimal. Well, that's why we get worksheets. But it always surprises me, everybody, no questions, you lecture, and we're doing exactly the same thing that we did Monday, right?
And as far as what says hexa, they count 0 as one of the digits.
Yeah, but because it's a number. I can't have a number system without a 0 in it.
But when it comes to actually write everything out, you start with the number 1 as the first digit. So
You mean this power right here?
Yeah, power.
Well,
no, not the power, the actual digit. So whenever you start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, Alpha, Bravo, or ABC, I was starting with 0 sometimes because of how it was labeled as hexa. So I guess I was confusing myself.
Every numbering system has to have a 0 in it. Mm-hmm. Okay. So that means I'm trying to write a number 10. So it's got to have a 0 in it, right? So every numbering system's got to have a 0. Now we get our 0 by putting a 0, right? Understand? But a 0 can be anywhere in the number. So I could have, like this is a base 10 number. You can put as many zeros as you want to. It's just that 0 has no weight to the value of the number. So this would be 10 to the 0, right? And this would be what? 10 to the first. Well, when I did this math, I would just ignore these guys that have 0 because they have no weight to the value of the number. Now, even on a decimal number, what digit determines if it's an odd number, and what digit determines if it's an even decimal number? The first one. And that's true on the binary system right here, right? But what's nice about the binary system is that if it's a 0, if that bit 0, we call that bit 0, by the way, because it's a 2 to the 0 slot. One thing you got to get used to in computers is 0 means something. And the analogy I use is that sometimes you see a field goal kicker or something that wears the number 0 on their jersey. It don't mean they don't exist, because it means something, right? You understand that? So in addressing, a device could have an address of 0 because it's a location, right? It's just that 0 doesn't have a weight. That makes sense? So all our numbering systems, normally we start counting from 1, right? You understand, which is legal. But when we start writing the number of digits that's available in a numbering system, the number of digits will always start with what? 0. But it starts with 0 because that is a digit. That's a digit. It's just when I go to an equivalent weight, that 0 has no value in the number. We say it has no value, but what it does is it shifts that sucker from here, which it would be, so this would be 10 to the second, this would be 10 to the third. If I didn't have that 0, I would lose the whole power of 10, right? You understand that? But it also determines the position. So guys, we could do these all day long. They do exactly the same thing, right? You understand that? Any more on here you want to work? So we went from what? We went from octal to decimal. We went to octal to all the other 3 bases. We went to decimal to the other 3 bases. We went from binary. We went from octal. So we went over one of these on each group. Okay, we'll do that 1, 2, 6, 7. From octal. 1, 2, 6, 7. Base 8. So we'll go to binary using groups of 3s. 1, 2, oops, wrong base, Rich. 6, 7, base 2. Everybody see how I did that? Are we okay? To get the hex, I'm going to take that binary number and I'm going to split it into groups of 4s. 2, B, 7. Are we okay?
Basically, whichever one of you pick up is really got to start from binary. You really got to go back to binary.
If you want to go to decimal, it's easier. I mean, you could take this number right here. So I could take this number right here. I could go to decimal. This is going to be 8 to the 0, 8, but you're going to have to use the calculator. 8 squared, 8 to the third. That's going to be 1 times the decimal equivalent of what 8 to the third is. Now you can use your chart. What's 8 to the third? 512. That wouldn't be too hard. Then I'd say plus 8 to the 2 times 8 to the second, which I can do that. That's 64, right? Plus 6 times 8 plus 7. Now I can just write this number down because I know any number raised to the 0 power is itself. I mean, is 1, right? Then I could do that math. Now I'm moving from adding to multiplication. And you can convert these over, you'll get exactly the same answer.
Okay, instead of doing the powers like this, back over the options, can we do it like, can we write the power of 2 out over the binary?
Yeah, that's what we're saying. You could do it this way. So I could take a big hex number, F39C, and that's going to be 15 times what? 16 to the 3rd. You got your chart over there, guys. 16 to the 3rd. 4,096. Then I could say plus 16 squared. That's 256. Plus 9 times 16 plus 12. I could do it that way. But now, by George, I'm not going to be able to do what? And you would come up with the same answer as you would if you convert it with binary. So that's the trick of it, right? Y'all understand that? So what we do to get a numbering system into the decimal numbering system is we use decimal equivalents of all these numbers and we multiply it times. Y'all understand that? So you could do this. So this is what's actually going on, but it's so easy to go to the binary numbering system. Between octal and hex, it's so easy, I don't need to do that. Because once I've got it into binary, then I can do what? I can do the 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. Now I'm dealing with adding, right? I'm not dealing with multiplication, I'm dealing with addition. Hopefully everybody in here can add. Most people can multiply, but when you get something like, 15 times 4,096, and then the next base, what's 16 to the 4th? That's 65,536. So now I could possibly have F times 65,536. Now, by George, that's going to take what? That's going to take time. So what we're doing is we're going to binary. Now I'm dealing with a sequence where I don't go from 1 to 16 to 256 to 4,096 to 65,536. It goes what? 1, 2, 4, 8, 16. And most people can do the powers of 2s almost in their head. You just do what? Just double it. But if you can't do it in your head, no, everybody can just write down, say 256, because 512, and over here on the side, just multiply it by 2. Now we're just multiplying by what? By 2. But guys, after you learn it for a while, though, you get those powers of 2s. You start getting them up to a pretty good place. I have it pretty good up to 65,536, and then it's 132,000. 131,000 something. So I'd have to write that down. But if I dealt with big numbers, I would learn more powers of 2s, right? You understand that? So what would this be? So I went from what? I went from octal to binary. I went from binary to hex, and then I'm going to go to decimal. So what am I going to add together? Now I'm adding 512. I'm adding 128. I'm adding 48. Some of the math you can do in your head, right? So 32 and 16, right? 48, and then 7. And then I add those together, and that'll give me my decimal equivalent. I know it's supposed to be odd. I know my answer is supposed to be greater than what? 512. I know I'm expecting an odd number. But if I come up with something that's less than 512, I know I did it wrong. If I come up with an even number when I expect an odd number, I know I did it wrong. If you come up with something 500, above 512 and it's odd, it don't mean it's right, but at least it's got a chance of being right? That makes sense. Okay, guys, y'all go ahead and take a 10-minute break.